All right, welcome everyone to this seminar today. Our speaker is Nikola Milićević, who will be telling us about homotopy and singular homology groups of finite digraphs. So, Nikola, the floor is yours.
Thank you, Bastian, and thank you to all the organizers for inviting me to give me this opportunity to give this talk. So this is joint work I've done over the last year and a half with Nick Scoville. Basically, the idea is to try to develop homotopy theory that's compatible with some homology theory for finite digraphs. What exactly do I mean when I say a finite digraph? People might have different ideas of what it means, so let me just be very clear what I'm talking about. I just mean a set with some relation that is reflexive, and finite just means the set is finite. There's several ways to write this information. Sometimes you'll see people write belonging to a relation like this. Sometimes they just skip the inclusion from set theory and they write it like this. But we can also write it in a visual way by saying that A is related to B if there is this directed edge we can draw from A to B. So I don't assume a priori anything on the relation except that it's reflexive. So in particular, I technically do have all these loops, but I will not be drawing them for simplicity. So, but they're always there in the background. If the relation is symmetric, then I'm going to say I just have a graph without the directed part, and I'm not going to draw directed arrows going both ways. I'm just going to draw a single edge connecting the nodes in the graph or the vertices. There's ways to map graphs to graphs using graph morphisms. Basically, it's a map on the vertices that sends edges to edges. The important thing here is sometimes when people say graphs, they mean one-dimensional CW complexes or some kind of one skeleton of a simplicial complex. I do not mean that. I honestly mean it's just a finite set with some relation on it. So there's no continua here. It's just a very small finite set. So examples like this come naturally in applied topology. For example, when you construct the Vietri strips complex in persistent homology, or in digital topology, digital images are examples of these symmetric relations. So I think there's a lot of interest to try to develop analogs of algebraic topology for these data structures. In particular, there is a connection between finite graphs and finite topological spaces. If you additionally assume that the relation you're talking about is also transitive, then you actually have something called a preorder. A preorder is just a reflexive and transitive relation in a set. And given a finite topological space, you can always define a preorder on the elements of that space. So you can say that there is an edge from X to Y whenever Y is contained in the closure of X. So this is how you would, for example, this is how you can define preorders on topological spaces. Conversely, if someone gives you a finite preorder, you can declare all the downsets in the preorder to be the open sets of a topology. What do I mean by a downset? It just means a set that's closed downwards with respect to the preorder relation. And this is an example of something called the Alexandrov topology. And the important thing here to note is that these two operations are kind of inverse to one another. So that there is an equivalence or isomorphism of categories here at play. So every finite topological space is equivalent to such a finite preorder. Let me give you some examples. If you, for example, just have the set 0, 1 through n with the obvious total order, this relation is going to define what the open sets in a topology for this preorder are, and these are the downsets, meaning just intervals from 0 to I for some I. So these are all the downsets. This should be closed sets. Apologize. So the closed sets will be the complements. So they will be these upward closed intervals. For example, these two are really the same pre-order. What I'm doing here is I'm just drawing the edges differently to illustrate the point that even though these are finite spaces, they might have some interesting topology hiding in the background, because you can, if by just simply redrawing the edges in a different spatial position, you see that there might be something like an empty square there. There might be a cycle. And it's very straightforward. You can find what all the open sets and the closed sets here are. They're just the downsets and the open sets. They're just downsets and the upsets. So as topological spaces, we have a notion of a homology theory for them, right? These are maybe not simplicial complexes, so we cannot use, for example, simplicial homology. However, we can use singular homology from algebraic topology to define a homology theory for these spaces. So we can declare the end chains of a finite space, or just any topological space, to be continuous maps from the standard n simplex into your space. With the standard boundary operator, this gives rise to a homology theory. So as an example here, I have an example of a delta 1, just a line segment from 0 to 1, and I have a finite space on the other side. The open sets here, if you just compute them from the relation, will be the empty set, and basically if I call this A and B, it's just the whole set. So this is an example of topology. So in particular, this map that I used colors to illustrate is a continuous map. You map all the blue points to the blue vertex, you map all the red points to the red vertex. But there are many such maps. You could have made different choices where you chose these cutoffs. For example, you could have also mapped all the rational numbers on the interval to the blue point and all the irrational numbers to the red point. The point is that these chain groups are often infinite dimensional. So even though you can define a homology theory, it's very hard to compute in practice, even for finite spaces. The classical solution is to never actually work with singular homology. You always replace what you're studying with some CW complex or simplicial complex in a nice way that somehow maybe preserves some homotopy. And then you start computing the simplicial homology groups of that object, or cellular homology if you're working with the CW complex. And it turns out that finite spaces are typically not homotopy equivalent to a CW complex. It's a very technical reason, but finite spaces are typically not Hausdorff, and CW complex is Hausdorff, so it's very hard to find maps between these two that are not constant, that will preserve homotopy types. So the classical solution then is the next best thing, and it came from McCord in the 60s, where the idea is to replace your finite space with a simplicial complex and show that you have a weak homotopy equivalence between the geometric realization of that simplicial complex and the space you're working with. The simplicial complex McCord considered was something called the order complex. And the simplices in the order complex are, remember, a finite topological space. You can think of it as a pre-order, or if you insist it's T0, it's a partial order. So you can just find all the chains that you have in the partial order, and you declare those points to represent a simplex in your abstract simplicial complex. And there is a map from the geometric realization of that simplicial complex into your finite space. The basic idea is whenever you have such a simplex, you will map everything in the interior to the point with the lowest index with respect to the partial order that you have on your space. So in this particular example, everything in red, remember the geometric realization is a continua, there's infinitely many points here. So I have to map, so the way the map works is you map everything in red to the vertex in red. Then you'll map everything in orange to the vertex in orange, and you map everything in blue to the vertex in blue, and everything in green to the vertex in green. This is the way this map works. And what McCord showed is that this is a weak homotopy equivalence. And in particular, it preserves homotopy groups, induces isomorphisms on them, but also it's going to induce isomorphisms on homology groups. So even though the singular homology of these finite spaces might be complicated, with this result, we can actually compute these effectively by replacing these objects with the simplicial complex. The important thing to note here, and what's surprising, is that this shows that finite spaces can have surprisingly complicated homotopy and homology groups, because you can imagine that you can construct a partial order such that its simplicial complex, the order complex, will have very interesting homology, which was very surprising, I think, at the time. And the basic idea of this work that I'm talking about is to generalize this result to when you don't require your relation to be a partial order. So I want to drop the transitivity requirement, and I also want to sometimes allow maybe bidirected edges, so going in both directions. So just as an example, we already saw from the previous slide that this partial order, if I were to redraw it, and so it's easier to see, has the weak homotopy type of an S1. You can kind of do this construction iteratively, so you just keep adding like the same copy below, and you will see if you just redraw the edges in different spatial position, you will see that maybe this is the suspension of the previous example. So you get this regular octahedron as an abstract simplicial complex. For example, this edge here would correspond to this edge here. I'm not drawing it there because it's a transitive relation, so I'm assuming it's transitive, but it would be very complicated to draw all the edges. But you can maybe see that you will have these in the order complex. You will have these triangular faces, so you will actually get a void. You will actually get the weak homotopy type of an S2. So the very first step to generalize McCord's result from partial orders and their associated order complexes is to define some simplicial complex on directed graphs that's going to generalize the order complex. So if we have an undirected graph, a very standard construction is the Vietri strips, or the clique complex of the of this symmetric relation, or the undirected graph. Basically, you find all the cliques that are subgraphs. Basically, you want everything in that collection to be connected to everything else in that collection. So different people call this by different names. It's known as the clique complex, or the flag complex, or the Vietri strips complex. And the idea is to generalize this construction to directed graphs. So I will say we have a directed Vietri strips complex associated to a directed graph, and it consists of all simplices of all points in X that for which I can find an ordering going from 0 to 1. I can label the points from 0 to n such that whenever I is less than j, I will have a directed edge from xi to xj. Okay. Notice that because I'm allowing bidirected edges in some examples, these orderings are not necessarily unique. I'm just requiring to find one such ordering. Okay. This is an obvious generalization order complex from the previous page, because if you have a partial order, this definition will coincide with the order complex, but it also generalizes the Vietoris-Rips complex from flat topology. So it's kind of like a bigger, more universal or unified framework. So the idea is to try to generalize McCord's result involving finite digraphs and this simplicial complex. For simplicity, I'm just going to drop the arrow above the letters VR, and I'm just going to write VR whether I'm talking about a directed graph or a undirected graph. It's going to be clear from the context. Some examples. So in the first example, we actually have a partial order. You can maybe quickly see that this relation represented by these edges gives you a transitive relation, because you have this diagonal there in the middle. And its order complex, or what I call now the Vietoris-Rips complex, will just be this square with both of these triangles filled in that are separated by the diagonal. Because you will have this particular chain, you have A less than B and B is less than D, and so therefore A is less than D, so you can fill this in. But now this construction allows us to generalize this to other relations, which are typically not transitive. So for example, we have this example for directed Vietoris-Rips complex and the one below. And I want to reiterate here that one might think, okay, if I have a directed graph, why don't I just take the transitive completion of it to get a partial order and then do the construction of the order complex? Well, this example shows you that you might actually destroy some homotopy types by doing that, because this example here, its transitive completion is the partial order you have at the very top, because you have to add this diagonal to have the transitive relation. But you will see that the homotopy type between these abstract simplicial complexes is definitely not preserved, because you will have a hole at the very bottom example, but you will not have a hole at the very top. So you really don't want to consider directed graphs as topological spaces or replacing them with a topological space, because you might destroy some homotopy structure that's there. So main goal is, given a finite digraph, we want to show that you can always construct a weak homotopy equivalence between the geometric realization of the directed Vietoris-Rips complex of the finite digraph and the finite digraph. There's a problem and maybe a reason why this hasn't been done since the 60s, when McCord actually got his result. This is a topological space. As I said, the digraph is not a topological space. What is a map between something that's a topological space and something that's not a topological space? So this is not obvious. Even if you have such a map, what does it mean for such a map to be a weak homotopy equivalence? This is not obvious. And like I said, digraphs are not topological spaces, so is there even a homology theory for these objects? So these are the questions we had to address to solve this problem. So you have a topological space and something that's not a topological space. Perhaps the immediate idea you have is, why don't we find a category that contains graphs and topological spaces as full subcategories? Then we will know how to map topological spaces to these other objects that are not topological spaces in this bigger category. That's exactly what something called check closure spaces allow us to do. If you're familiar with topological spaces, it's not too hard to get accustomed to closure spaces. You have these axioms that are equivalent to defining a topology typically. You have a set and you want to define a closure operator on the subsets, and you want the closure of the empty set to be empty. You want it to be expansive, and you want it to respect unions. If you also require that the closure applied twice to a set gives you the same result as applying it once, meaning that the closure operator is idempotent, you will get something called a topological closure operator, which is equivalent to actually having a topology on your space X. So we will not be requiring this axiom, and we'll just stick with the first three. And that's how you get a closure space. So that's how topological spaces fit inside as a full subcategory. And it's very easy to see that directed graphs can also be embedded as a full subcategory of closure spaces. Given a directed graph, I can define the closure of a vertex to be all the outgoing neighbors of that vertex. So all the points Y that you can reach with a directed edge from X. Then the closure of a subset will be the union of all these things that belong to the set. So for example, here, the closure of A will be A, B, C. Remember, I always have the loops, even though I'm not drawing them. That's why I have A in there. So this is good. And we can also, once you have a closure operator, you can also define closed sets. Closed sets are the fixed point of the operator. And in particular, in this example, these two digraphs, they happen to have, you can very easily check from the definition that they happen to have the same collection of closed sets. Therefore, if you were to use the typical definition of continuous maps that you have topological spaces, you would have to declare that the identity map here is continuous. But we do not want that because there's an edge here that's not being mapped. That's not being mapped to an edge. So this is not the definition we want. We want to generalize the definition of continuity to all closure spaces. And it's the following one. You want the image of a closure of a set to always be contained in the closure of the image. For topological spaces, these two definitions are equivalent. But when you go to this higher category, they're not, and you need to make a choice which one is the right one. And if you want to generalize graph morphisms, you have to pick the top one. So this is the definition that we will be sticking with. And this is very nice because it immediately allows you to import a lot of language from topology into the setting of directed graphs. You can define neighborhoods, you can define closures, you can define interior covers, which you should think of as the best approximation for open covers that you can have for directed graphs, which can be very useful in applications when you're considering nerves and so on of your space. I don't think I have much time to focus on the actual definitions here, but maybe I can come back to it if anyone's interested. So the important thing, now that we know how to map a topological space to a finite digraph, what does it mean to have a homotopy of such maps? Well, we have some closure space, which can be some finite digraph. We also have the standard unit interval 0 to 1 with the standard topology. We can take a product in this category to construct a cylinder object, which then allows us to define a homotopy between maps, between these closure spaces. Likewise, we can define higher homotopy groups to be homotopy classes of such maps from when the domain is a sphere into your space. And finally, we will say that a map between closure spaces is a weak homotopy equivalence if it induces isomorphisms on all homotopy groups. So these are very natural generalizations from topological spaces to this bigger category. Likewise, we can also define homology groups of finite digraphs. I have the standard n simplex. I can consider continuous maps from the n simplex into my finite digraph or any closure spaces really. And I can consider the chain group generated by all such maps. We have the boundary operators, the usual ones, and we can define homology groups. So we've done everything. We kind of solved all the obstacles to our main goal, which is define a way to map topological spaces to something that's not topological, what does it mean for such a map to be a weak homotopy equivalence? And is there also like a homology theory for these spaces that, we can maybe calculate? Just like with topological spaces, these chain groups are typically infinite dimensional because you have just way too many continuous maps from the standard n simplices into your space, even if your space is finite. So this is why we need an analog of McCord's theorem, because otherwise, we can define these groups, but there's just no way to calculate them. We have nice theoretical results, though. We can show that this homology theory is a homology theory for closure spaces in the very same sense as in the sense of Algebraic standard axioms. It satisfies analogs of all of those. So, for example, you have excision axioms, you have the dimension axiom, you have homotopy invariance axioms. So it's a very nice homology theory. If you have an interior cover, you also have Meyer-Vietoris long exact sequence. So, for example, if you have a graph, this means you can split it into smaller graphs. As long as the smaller graphs form an interior cover, you can calculate the homology groups of those smaller graphs and combine them to see how the homology group of the bigger graph fits into this framework, which is nice maybe for if you have ideas for algorithms, you can parallelize computations of homology groups in this way. Likewise, you also have analogs of the Hurewicz theorem that if you have these maps from homotopy groups into homology groups, and if your space satisfies some connectedness axiom, you will get that this map is an isomorphism. So our very main result is the construction of a map between the geometric realization of the Vietoris-Rips complex and the graph you have in question. I think a picture is maybe better to focus than the definition that's written there. Basically, suppose I give you this finite digraph. This thing on the left, I hope you believe me from everything I've told you so far, is the geometric realization of its Vietoris-Rips complex. And I'm basically telling you with colors what you're going to map to what. The idea is, if you're familiar with Voronoi diagrams, you will basically find these points in the simplices that are closest to a particular vertex. And so, for example, this is the stuff in red is the Voronoi cell corresponding to the vertex x0. And you will map everything in that Voronoi cell. These are all the points that are closest to x0 to x0 as in its image in the graph. There's an issue of what to do when you have a point that doesn't have a unique point it's closest to in the graph. So at these boundaries of Voronoi cells, what do you do? Well, this formula gives you the answer is you always make the choice to go to the one with the highest index in the order. There is an issue when you have bidirected edges, because there might be different choices you make as you move up the skeleton when you define this map inductively. I'm not going to go into the details, but we show that these choices don't matter. No matter what choice you make, even if you have a bidirected edge, on the boundary, you can maybe map up. You can maybe make different choices as you move across the skeleton, as long as overall you're mapping points in the Voronoi cell to the point that corresponds to the Voronoi cell, you'll be fine. And we claim that this map is a weak homotopy equivalence. In particular, this will imply that the singular homology groups of finite digraphs that we're talking about and the higher homotopy groups can be effectively computed by replacing the finite digraph with the directed Vietoris-Rips complex. So this there's this observation in applied topology, more specifically TDA community. If you have some finite metric space as a subset of Euclidean space, and you consider growing closed balls around each point in your metric space, typically people consider two different filtered simplicial complexes. You have the check complex corresponding to this filtration, or you have the Vietri-Strips complex corresponding to this filtration. The check complex is basically the nerve of this cover of the space by these balls you have. And because these are balls in Euclidean space, they're nice and convex. So all their intersections are also nice and convex, therefore they're contractible. So all these simplices that correspond to the check complex, they come from these intersections of convex sets. And the nerve theorem tells you then that the geometric realization of the check complex is homotopy equivalent to the union of these balls. And that's sometimes why, at least when I was in graduate school, people would mention that the Vietri-Strips complex, it might be faster to compute than the check complex, but the check complex has this nice property that it kind of preserves the homotopy type of this cover that you create. This is not true for the Vietri-Strips complex because, for example, if your points live in R2, you can very easily find examples of Vietri-Strips complexes that have homology groups that are non-trivial in dimension higher than 2. So this clearly cannot be the case. And I think the work by Henry Adams as well shows this, at least when considering the Vietri-Strips complexes of the circle. However, what we show with our result is that the Vietri-Strips complex doesn't necessarily have to preserve the homotopy type of this cover by balls. It will have the same weak homotopy type as the underlying graph you construct by defining a relation on your points by saying that x is related to y if and only if the distance between x and y is less than r. So the Vietri-Strips complex will have the same homotopy type as this graph you construct, but might not necessarily have the homotopy type of these, the union of these balls you use to construct the check complex. This is also these results also allow us to effectively compute a lot of homology groups of, for example, these roots of unity, where I think of these roots of unity as points being sampled from a circle or some sphere, and I have the closure structure or the graph structure is you're adjacent or there's an edge to some many nearest neighbors on the circle or on the sphere. We had a lot of issues computing these singular homology groups by hand because they're infinite dimensional, but you could still do some computations, even though for many of these parameters, there's gaps. We didn't know what happens. And this new result actually allows us to compute all of them for all parameters n and m as we can just replace the underlying closure space or the underlying graph with a directed Vietri-Strips complex. I have thought a bit about, we have, in TDA, we have the Vietri-Strips complex, and we typically consider the Vietri-Strips complex when we consider computing persistent homology. What about if instead of a metric space, you have a weighted digraph? So instead of like a symmetric matrix that represents distances in some finite space, what if instead you have just some weight matrix that corresponds to some weight you put between points? It doesn't have to be symmetric. So is there a way to maybe consider algorithms to compute the persistent homology of filtrations of such weighted digraphs? And I thought about it for a bit, and then I did some literature search just to make sure I'm not reinventing the wheel. And very recently, Muranov showed that the Alexandra homology, which is basically the same as the singular homology when you have a poset, when you have a finite topological space. And pad homology agree on posets. So pad homology seems to extend the singular homology of posets to general directed graphs. And my conjecture is that you can use very similar arguments to show that pad homology agrees with singular homology that I've been considering for directed graphs. I think you can maybe adapt the arguments verbatim from this paper just to in a slightly generalized fashion. And there is also recent work that allows you to compute persistent pad homology, or at least some grounded version of persistent pad homology. So this would basically correspond to maybe computing the persistent homology of such weighted digraphs. But these are two works from two different basically groups, and there might be some there might need to be some language translation between them to actually, make sure everything works properly. So I think that, yes, relying on previous bodies of work, you can consider an algorithm for computing these persistent homology of weighted digraphs. So now comes the punchline. I've kind of been lying throughout the whole talk. I told you that you need to go to closure spaces. Turns out you need to go to an even bigger category of pseudo-topological spaces. But the definition is a bit more involved, and the definition, instead of generalizing a closure operator, it's generalizing the idea of what it means for a filter to converge to a point. It's very technical, and I don't want to get into too many details. I think the closure space perspective is very nice. In particular, every finite pseudo-topological space is a finite closure space. So every finite digraph automatically is a closure space. However, we do need to consider this bigger category because in a lot of our proofs, we are considering very they rely on a lot of standard homotopy theory arguments, and the category of pseudo-topological spaces is simply much nicer for doing homotopy theory than closure spaces are. For example, pseudo-topological spaces are a Cartesian closed category, while closure spaces are not. So, for example, you immediately have mapping cylinders, so you can replace every map that you have with the cofibration, which is very nice for homotopy extension arguments. We also have to make sure that a lot of classical results from algebraic topology do carry over to this category to allow us to prove our results. So we did all the heavy lifting there as well. And this is kind of the takeaway. You have the topological spaces we all know and love. There's like a friendly kitten. Closure spaces, maybe you have to bite a bullet a bit to learn the theory. Maybe the kitten has 3 eyes, but it's still a kitten. It's not too far away from topological spaces. Pseudo-topological spaces are like this monstrous kitten. They might look scary at first, but I claim that they still have very nice properties that are very useful for proving theoretical results. But for computational reasons, if you're only working with directed graphs, you only need to concern yourself with the middle layer of this picture. I just wanted to give some references. So we have this work is currently now on arXiv. There is very recent work that was done in parallel to us using different arguments that also shows that. So Jonathan was considering only undirected graphs. Our work also works for directed graphs, but we also showed that the Vieta-Ristrup complex always also has the homotopy type of its underlying undirected graph by also considering arguments using pseudo-topological spaces. And we also have some published work on very general homotopy and homology theory of, and even persistent homology of closure spaces from my thesis. And I think that's about it. I think I'm out of time, so I can maybe stop here, take questions.
Thank you very much. Let's all unmute briefly and clap for Nikola. Thank you very much. Are there any there are questions from the audience, please unmute yourselves and speak up. There are, I think, no pressing questions in the chat. There was something about the sound issues, but this has been resolved. So is there anything people want to know directly from Nikola?
I'll ask a question, Nikola. So certainly you proved theorems about pseudo-topological spaces, but for the main results you presented today, is it correct to say that most of those main results can be stated just using closure spaces, but then the proof might use pseudo-topological spaces?
Yes. So for example, the map I gave you, the one using the Voronoi cells, definitely is a map of closure spaces. However, when considering its weak homotopy type, I think you have to consider the weak homotopy type of all pseudo-topological spaces, right? But the map itself is a map of simply closure spaces. It's not a map of pseudo-topological. I mean, it's a full subcategory, so it is, but you don't have to talk about it in that way.
Any other questions? Otherwise, I'm gonna. I had one about the computational aspect. So you mentioned the persistent homology things in between, but how hard are in general some type of computations here? So is that feasible? I mean, in normal persistent homology, we know, okay, we do this boundary matrix reduction, then we're done. But how hard are other computations here? Do you have a feeling for that?
Yeah. So I think this paper, there's this very old work on directed networks by Samir Chowdhury and Facundo Memoli on computing pad homology. I'm not sure in what dimension. Maybe there was like a bound. They were maybe only considering a couple of dimensions, or maybe all of them. I'm not too familiar with pad homology literature, unfortunately.
Is that with the Doppler complexes potentially? Sorry for interrupting.
Oh, no. So it's this idea of pad homology, and I don't think it has much to do with Doppler complex construction. It's just a way to define a chain complex on directed graphs that
I see, yeah.
that's trying to generalize the idea from simplicial chains from topological spaces maybe, but also to consider higher order relations than just like than just direct neighbors. So my understanding is that there is an algorithm to compute path homology, and this grounded persistent path homology is, I think, a modification of this original algorithm by Facundo and Samir. I haven't played with path homology at all, so I can't tell you how many points or what's the size of a digraph you can consider on a local machine or anything like that. But it's out there in the literature. I'm sure they have reported this somewhere.
We now have a question from Zaira. Hopefully I'm pronouncing that right. You can also read the question yourself, of course, but just going to read it here now. Has this concept been applied on any real-life application yet?
So by concept, do you just mean the Vietri-Sips complex, or do you like
my interpretation would be the in general this whole notion of the digraph formulation. But I didn't ask the question. Yeah.
Oh yeah. Okay, I'm gonna assume it means that. So yes, this particular paper talks about a lot of applications where you might have directed networks and the need to compute some kind of algebraic structure like a persistent homology on top of them. Yeah, so I think just if you were consider like a random Erdős-Rényi graph, like it doesn't have to be symmetric. So I think just on average you can expect like a graph in nature to be directed, but also many I think social relations can be considered as directed graphs, like friendship, for example. Like maybe you consider a person to be your friend, but maybe they don't consider it to be their friend. I don't know how you record that, but But yes, I think this paper has like a nice survey of applications of directed graphs.
I'll ask another question. So you prove this nice weak homotopy equivalence. Is there any chance it's a homotopy equivalence, or does that not even make sense in this context?
I mean, there is, but the issue is the same as the issue McCord had, right? Typically, the finite digraphs will not be Hausdorff. The geometric realization of the Vietri-Strips complex is always Hausdorff. So to have a continuous, you can have a continuous map going this direction, which is the one I'm giving you. But typically, to go the other direction, you will only have constant maps because of the non-Hausdorff nature, right? Basically, if the space in question has non-trivial homotopy, constant map will not be a weak homotopy equivalence. In general, this is just not true. Yeah.
Right.
This is really the best you can.
Mm-hmm.
Very nice. Any other questions for the public session? If not, let's thank Nikola again. I'm gonna stop the recording. So thank you very much for a great talk. We have another question. Or is that more of a comment? Maybe you want to read that yourself. Please feel free to unmute.
Yeah. Oh yeah. Go ahead.
No, I meant the person who asked the question.
Yeah. I understood. Yes. Sorry. Yeah. Yeah, I'm not sure. I haven't really thought about Morse theory. Yeah, I'm not sure.
Yeah. So the question was whether the homology of the digraph can be connected with Morse theory, since there seems to be a relationship between gradient vectors and so on. But I have to say, this was a comment by an audience member. I'm not an expert myself in there, so I'm also just reading it off. Any other questions? Then let's stop the recording here, and thank you very much. And let's move into the non-recorded session. Thank you so much, Nikola.
Thank you for having me.